Hey guys, in this video we're going to take a look at a couple of more examples in terms of voltage division and how voltage divides continuously throughout the circuit, and we're also going to take a look at how current also divides throughout the circuit as well. So this is actually from the first schematic that's in basically the example problems for voltage and current division. This is posted on eLearn, so you guys should be going over this and reviewing before, in addition to looking at this lecture and working through the problems to make sure that you're coming up with the same calculations that I do. So if you guys understand how these problems work and how the solutions are derived, you should really not have any problem whatsoever with test one. Anytime we actually take a look at more essentially complex schematics in terms of more loops or more branches, the material itself, if we're looking at further division of voltage or further division of current, the problems really are not that much more involved in terms of the conceptual understanding of how voltage and current divides. It really is based off the nodes within the circuit and also being able to relate each element in terms of their series and parallel, relationships based off those nodes. So the material, as the schematics get bigger, the material doesn't necessarily get more complex, it just gets more involved. So understand the difference between complex concepts and then just involved work. So I like this packet that I put together for the students because it really just kind of gives that foundation of how voltage continually divides and how current continually divides. And we're going to see an example of where we're going to have to do voltage division not once but twice, and then we're also going to see how current divides in an outer loop with the first problem. In a different video we'll look at problem number 2, but for this one we're going to take and basically just do this as our voltage current division, the first problem, the first example in that packet. So here we got a 10 volt source, we got a 30 ohm resistor, a 60 ohm resistor, but I redrew the circuit in a different way just so for those, for students who are just now starting to take a look at these schematics, I wanted to actually just redraw it to just help with our understanding of the nodes within the problem and also the relationship of the elements. So this is an equivalent schematic to the one that I've put together in that packet. And so the only difference is that I kind of redrew these two parallel elements and these three parallel elements just to kind of give a better visual, to just help you get used to seeing basically these relationships between the elements. And so first thing we're going to take a look at here before we go any further is we're going to look at the nodes for this circuit. And for this one we're actually going to be looking at the current through the 45 ohm resistor and also the voltage across the 80 ohm resistor over on the right hand side. But let's look at the nodes first. So let's take a look at the 10 volt source and 30 ohm resistor. Sure enough, they're in series because we have two elements exclusively sharing that one node. Same thing down here with that 60 ohm resistor. Let's take a look at this guy here. So we got 30, 45. That has a common point of connection, sure it does. And it's also connected to the 25 ohm resistor, but there's nothing in between the 25 ohm and this point right here. So that's also one node. And if we look above it, that actually exists as the same node as well because we actually have no elements in between basically the 25, 20, and 15. If we look on the right hand side, sure enough, there's no elements in between, so it would suffice to say that the 25 ohm resistor, the 20 ohm resistor, and the 15 ohm resistor are all in parallel with each other. And this node is actually also the same as the one that connects down to the 70, but just to show the relationship, 70, 80, sure enough, are both in parallel with each other because there's no element in between the top and the bottom nodes. Okay? So down here, that's also the same node that connects all the way to the 45 and 60. But just as a reminder, when we're talking about series elements, here 60, 10 volts, and 30 are effectively in series with each other because 60 shares an exclusive node with 10 volts, and 10 volts shares an exclusive node with 30 ohms. So they're effectively in series with each other. But this relationship between 30, 45, 25, 20, 15, since they're all connected together, There's no definition for that. It's just an undefined point of connection. That's all it is, just connected. And here, same thing, 60, 45, 70, and 80. The bottom nodes are actually all connected to each other, but we don't have a name, again, for that relationship, so it's just undefined. So, first thing that we need to do is start breaking down the circuit, because if I want to find the voltage over here, the 80 ohm resistor, it's going to actually divide from somewhere over here. So we actually need to break down the circuit and see exactly how we could even start formulating visuals to kind of get an idea of where that voltage will actually divide. Now remember that voltage actually exists between any two given points within a circuit, and we did that with some of the initial problems within the first part of this class. So we're going to continually use this idea about how voltage will exist between 2 points, and that's actually going to help us continually see how voltage divides throughout the remaining portion of the circuit. But so the first thing we need to do is actually initially find a voltage that we're actually going to start seeing divide from the source. So we actually, in order to find Vx, the first thing that we need to do is actually find the voltage between these 2 points here. And that voltage is actually going to divide throughout the rest of the circuit. So these 2 points is the first voltage that we actually need to find. So first thing we need to do is actually break down the circuit to a single series loop. And once we break it down to a single series loop, then we can actually find that initial voltage that will then later on start dividing throughout the circuit. So the first thing we need to do, basically kind of start on the right-hand side. We have to collapse towards the source. So 70 and 80, those are readily collapsible in parallel. 25, 20, and 15 are readily collapsible in parallel. And sure enough, using the same formula that I showed you guys in previous examples, 1 over the summation of the reciprocals, 1 over 25 plus 1 over 20 plus 1 over 15, its inverse equals 6.38 ohms. And 70 and 80 in parallel, that's just 1 over 70 plus 1 over 80, 37.33 ohms. Now, see, remember how I told you guys just for 2 elements in parallel, I don't want you to remember that, that this equation here, R1 times R2 over R1 plus R2. Lots of people love to use that. I hate it, just because this is the only equation you guys need to know, because that works with any number of elements in parallel. So we get these 2 equivalences, and I always suggest this, like I've said in previous lectures, I always recommend redrawing the circuit, because as you redraw the circuit for the types of questions I'm asking you guys, we can actually easily have a map that we can basically go back and kind of start labeling, and it helps us build more of an understanding of the work that we're actually doing, and just it really just gives that good visual and reinforces your understanding and how these concepts are actually being applied right here. So sure enough, 6.38 ohms and 37.33. Let's look at the nodes again, right? Let's take a look at the nodes. Sure enough, when we combine 25, 20, and 15 in parallel with each other, that 6.38 ohms of equivalence became also in series with the equivalence of 70 and 80 ohms in parallel. So the combination of those parallel elements on the right and then also on the top right here took those 2 equivalencies and put those in series with each other. Now, let's take a little bit of a look right here, and I want to talk about just maybe a little bit of the, I don't know, let's think about this. And I want to talk about the nodes again. So sure enough, 60, 10, 30, that hasn't changed. But look at the left node of 6.38. Now, 6.38, that actually shares a node with 45 ohms. 37.3 shares the bottom node of 45 ohms. So whatever the voltage is across this 45 ohm resistor here has to absolutely be basically a voltage that's also going to exist across the combined voltages of these 2 series elements right here. Remember, series elements, they have the same current, different voltages. So the voltage across both of these right here is also the same as the voltage across the 45 ohm resistor. And so we need to go ahead, in order to find basically the first voltage across that 45 ohm resistor, we need to break down the circuit again. There's another thing that I want to make a note of. When we combine basically the 70 and 80 ohm resistor into the equivalence of 37.33 ohms, that 37.33 ohms of equivalence also shares the same two nodes as the individual 70 and 80 ohm resistor. So actually the voltage across the 80 ohm resistor is also going to be the same as the voltage across the equivalence of basically 37.3 ohms, which was basically 70 and 80 combined in parallel. Well, let's go ahead and break this down a little bit further and see if we can find basically a single series loop that we could find the voltage between these 2 points. And sure enough, 45's in parallel with the series relationship of 6.38 plus 37.33 ohms, so 1 over 45 plus 1 over 43.68. And that comes out giving us an equivalence of 22.17 ohms. So guys, here, let's look at the nodes once again. Wow, taking that 45 ohm resistor and then combining that in parallel with the series relationship of 6.38 ohms and 37.33 gave us an equivalent resistance of 22.17, and that exists between these 2 points. And that means that the same voltage of V1 that we defined right here as actually being between those 2 points is actually also the same as the voltage across the 45 ohm resistor. Let's look at this a little bit further in terms of intuition within the circuit. So here, if I personify myself as the 10 volt source, and I'm looking into this circuit right here, I don't see 45 ohms of resistance or 6.38 or 37.3, or I don't see 70, 80, 25, 20, and 15. All I'm going to see between these 2 points is 22.17 ohms. And so it would suffice to say that the voltage across the equivalence of 22.17, because that's the equivalence of resistance between these 2 points right here, then that's actually going to be the same as the voltage across the 45 ohm resistor that exists between these 2 nodes. The nodes of the 45 ohm resistance and the equivalence of everything to the right broken towards the 10 volt source of 22.17 is also sharing those same 2 nodes. So the voltage across the 45 ohm resistor is the same as the voltage across the 22.17 ohm equivalence, and that's also equal to V1. And V1 is actually what's going to continually divide throughout the remainder of this section of the circuit. So the first thing that we need to find is the voltage of V1, or the voltage across 22.17 ohms of equivalence, or the voltage across the 45 ohm resistor. So let's move it down and let's continue working the problem. So here I just went back, and even though I have this circuit drawn on the left-hand side, I want to make sure that we're referencing this appropriately. And so, just make sure I move the camera in the right position. Yep. And so here, V1, which is the first thing we need to do, is 10 volts. And then by voltage division is multiplied by 22.17. Remember, we're looking for the voltage across the 22.17 ohm resistance. And so that goes in the numerator for voltage division, divided by 22.17 plus 30 plus 60. And that gives us a voltage of 1.98 volts. And so the voltage between these 2 points here is equal to 1.98 volts. So this is the new voltage that we can think of that's actually going to divide between these 2 elements. See these 2 series elements. See these 2 series elements. You know, another way of looking at this. Let's actually redraw this real quick. because I think sometimes we can get better visualization right here. All right, so 37.3, 6.38. Sure enough, that's still V2, but this gives us a little bit of a better visualization here, guys, because now we really can see that these two series elements here actually, once we combine those two together, shares the same two nodes as that 45 ohm resistor. And so therefore, the potential difference between these 2 points is 1.98 volts. So that means that that has to divide between these two series elements right here. Remember, series elements have the same current, different voltages. So sure enough, once we actually have this voltage of 1.98 volts, then we can perform voltage division again and easily find the voltage across the 37.3 ohm equivalent resistance over here, and that is the same as the voltage across the 70 ohm resistor and what we're looking for, the voltage across the 80 ohm resistor. So V1 was equal to 1.98 volts, and that is equal to Vx plus V2, the voltage across each of these elements. They're in series, but remember their combination is in parallel with 45 ohms. So all I have to do, guys, is take that 1.95 volts, 1.98, ooh, 1.98 volts that we found at the very beginning, and now we just perform voltage division again and find the voltage across the 37.3 ohm equivalents. So 1.98 times 37.3 over 37.3 plus 6.38, and then that's simply going to be equal to 1.69, and that is in fact the voltage across the 80 ohm resistor. And it would make sense because you may look at this and say, oh, 1.69 volts, that's really close kind of to 1.98 volts. Does that make sense? And it does, because 37.3 ohms is way more resistance compared to 6.38 ohms. And so therefore, the voltage of 1.98 will divide more over here directly with that 37.3 ohm resistor, because it's going to take more work for current to actually get through that. Remember, voltage is the work needed to push that charge through that element. And so here we lose that potential. We lose more energy as we push current through that 37.3 ohms equivalence. Okay? Well, what about the current? And see how current can actually divide here. What about the current through the 45 ohm resistor? Well, let's go back and start with basically that source current. Now, we already took a look at breaking down the circuit into single series loop. If we go back to the single series loop that we had over on the left, we can easily find that source current, the current that's coming out of the 10 volts. Now, remember, this is the equivalent circuit, the equivalence to everything that we saw at the very beginning of the problem. So if we have a single series loop, and sure enough we can see that because each element is basically connected to its adjacent element by one single exclusive node. Excuse me. And so here 10 volts is connected directly to 30, 30 is directly connected to 22.17, 22.17 of equivalence is connected to 60. So it's easy to see that with the series elements here, they share the same current. So therefore, we can easily find Is. And sure enough, 10 volts is equal to V30 plus V60 plus V22.17. Obviously, since we're bypassive sign convention, current leaves the positive terminal of the source and goes into the positive terminal of our resistances. As we've said before, guys, by passive sign convention, we're denoting these voltage drops right here because we're losing energy as current works through the circuit. So here, 10 volts, that's equal to basically 30 times Is plus 60 times Is plus 22.17 times Is. And so that means that that source current, when we combine like variables, see, like as we said before, each element has the same current. We can easily find Is. Is is equal to 10 volts divided by 30 plus 60 plus 22.17 ohms. And that's equal to 0.08195 amps. So this is the current that's actually going to start dividing throughout the rest of the circuit. So let's take a look here. I'm going to go back to the circuit that's actually, well, right there. But let's look at it in terms of the currents. The current that leaves the 10-volt source is 0.08915 amps. So let's look at how maybe that will divide. Well, if we consider the fact that 6.38 and 37.3 ohms, they're in series. That series relationship is in parallel, as we've seen before, with the 45 ohm resistor. So in order to find the 45 ohm resistor's current, all we have to do is perform current division with the 0.08915 amps that left the source, because here we can easily see that that current will split between Ix and then Iy, in which also we see here Iy, because 6.38 and 37.3 are in series, that's the same current. So all we have to do is basically perform current division with that source current. Bam. 0.08915 amps. Remember, opposite goes in the numerator. We're looking for the current Ix through 45 ohms. So here, 6.38 plus 37.3, that series equivalence goes in the numerator over 6.38 plus 37.3 plus 45. And Ix comes out to be equal to 0.0439 amps. Let's go back and see if we can remember how to do this intuitively. Well, we already have the voltage that's across that 45 ohm resistor. It's the same as the voltage that we found for the 22.17 ohms equivalence. And that was 1.98 volts. So 1.98 volts divided by 45, 0.044 amps. Yep, worked just fine. Current division worked just fine. We had a different way of looking at it, just to make sure that we were able to go back and check our work to make sure that we know that we did it correctly and that our numbers made sense. All right. Well, in the prior voltage division portion of this problem, we saw how we perform voltage division not once but twice, and we can do the same as far as with current division. We found the source current, and we also were able to find the current through the 45 ohm resistor. But what about, we know 37.3 ohms is basically that 70 and 80 ohms combined in parallel. And 6.38 ohms is basically 25, 20 ohms and also 15 ohms combined in parallel. So we can go back and actually see in either one of these what the currents are that are dividing through those parallel elements as well. So let's actually take a look at one of the currents that's actually going to divide up here in the three parallel elements that make up 6.38 ohms of equivalence. All right, let's take a look. Sure enough, I redrew the circuit in such a way because I want you guys to see and just get that visualization here. Remember, it's not how the elements are oriented with each other as much as the nodes that defines that relationship. And so the current Iy, if we look back at what we just saw, is basically the current that goes through the 6.38 ohm equivalence and then goes into 37.3 ohms of equivalence. Here, we take that 6.38, we expand that out again by those parallel elements. And remember, parallel elements have the same voltage but different currents. And so sure enough, here, Iy, once it gets to these three parallel elements, it splits between all three of them. So Iy, sure enough, is actually equal to Ia plus Ib plus Ic. But what happens is that it goes through each element and gets over to the right-hand side here, and by KCL, they all three combine again back into Iy and then flow into the 37.3 ohm equivalence. Now we know that that's made up of two parallel elements, so that Iy reforms again, but then splits between those two. But for the sake of looking at the current Ib, I'm going to find right now, we're just going to say it just reformed, flowed through, and then went back towards the 60 ohm resistor. But here, if we want to find IY, that's the current that flows in and then splits between those three elements and then comes back around. That's equal to IA plus IB plus IC. So here, 0.08915 amps, just to find that really quickly, put opposite resistance in the numerator, 45 over 45 plus 6.38 plus 37.3. Remember these two, their equivalencies were in series with each other. That came out to be 0.0452. And sure enough, if we took a look at 0.0439 plus 0.0452, that came out to be equal. The combination of those, the addition of those, came out to be 0.08915 amps. So remember with current division though, current division only works for two elements in parallel. So if we have three elements in parallel, we actually have to go and combine the other elements in parallel and isolate also the element that we're actually looking for the current through. So we break it down in such a way that we have an equivalence in parallel with the resistor that we're looking for the current through. Now in this case, those two parallel elements we're going to combine is 15 and 25 ohms. So here IB is simply just going to be equal to 0.0452, and then 15 over in parallel with 25 is over 15 in parallel with 25 plus 20. Remember, because opposite resistance goes in the numerator. That value came out to be equal to 9.375 ohms. But if we say 0.0452 times 9.375 ohms over 9.375 plus 20, that gives us a current of 0.0144 amps. So that's another good example, guys, of how we can actually see current divide not once but twice. And if I gave you more loops within the circuit, let's just say I made this into 3 or 4 more loops, and you could take that and take these currents and just continually divide those as well. It's just a little bit extra work, but the concept is absolutely the same. So in the next video, we're going to come back, take a look at the second problem, and see what more we can find out from that to better our understanding of voltage and current division. See you then.